All right, so today's lesson is over dissociation and solubility curves. We're doing these out of order so we didn't have math back to back, but remember the term soluble means the same thing as dissolve. So if something is soluble, it's able to dissolve in a solvent. For ionic compounds, if we dissolve a solid solute through the process of solvation, that is what it's called, water molecules are going to surround the solid solute and break them apart from the formation of whatever crystal that they have made. And when that solute breaks into its ion form, we call this dissociation. So when those ions separate from each other, they are dissociated. The dissociation factor is based on how many ions the solute forms. The larger the dissociation factor, the more ions are formed. So it gives an example. Which of the following would you expect to have the largest dissociation factor? So you would figure out how many ions are in this and then determine it from there. We have a sodium chloride, which dissociates into 1 sodium and 1 chlorine. So that's 2 ions. Okay, let's compare that to the other ones. We have 2 potassium ions and 1 sulfate ion with 2 negative charge. You can find this information on your polyatomic ion list if you don't know it. So that's 3 ions total. We have KBr, which is going to be 1 potassium ion, and then bromine is 1 bromine ion. So that's 2 ions as well. And then our last one is CO2. It is a covalent compound, so it's not going to dissociate into ions. So this one is going to have 0 ions. Okay, so the one that has the most is going to be B, K2SO4, because it has 3 ions, therefore it has the largest dissociation factor. So you can figure that out based on how many ions are in there. We've counted ions before in formulas. You guys should know what that is. You don't technically have to write out the equation of them being separated, but if you can count those ions, you can figure out which one has the largest dissociation factor. If you pour a powder or any solid into a solvent, how do you get it to dissolve? Even if you start stirring, what will happen eventually? So usually, if we're pouring a powder into a solvent, we are going to help it dissolve by making it warmer, changing the temperature, increasing the surface area. So if it's a sugar cube versus sugar granules, the granules will definitely dissolve faster. Or if we are agitating the solution and stirring it, we can get it to dissolve a little bit faster. We talked about those factors previously when we were going over factors that affect solubility in our first set of notes. So you can do that if you are trying to get it to dissolve. Normally it'll just sit there if you don't do anything to it, and eventually over time it will start to dissolve depending on what substance it is and if it can be soluble. A saturated solution contains the maximum amount of solute for a given amount of solvent at a constant temperature. So this is where it reaches the max of the amount of substance that can be dissolved. Usually at saturation point, a solid starts to form, and above saturation, there's definitely solid present in that solution. An unsaturated solution contains less than the maximum amount of solute for a given amount of solvent at a constant temperature. So in this situation, it would kind of be similar to a dilute solution where we have the capacity to be able to dissolve more substance in this until it reaches the saturation point. So at an unsaturated solution, we can dissolve more substance in there. Supersaturated means that there is more solute than a solvent should theoretically hold. So we have reached the maximum at saturation point. Supersaturated, we're still over that maximum. And usually there's going to be a solid in there, and crystallization is the most common form of solid that forms in a supersaturated solution. So notice that the definition for unsaturated, saturated, and supersaturated are all a level of solubility at a given temperature, which means if the temperature is changed, solubility gets affected, which is where our solubility curves come in. Solubility curves shows the relationship between solubility in grams of our solute per 100 grams of water and temperature. We're going to label the following on the graph. There's a supersaturated section, a saturated section, and an unsaturated section. So on the top, we have supersaturated. Actually, on the line, This is where saturated is. Okay? So on the line is saturated. Above is supersaturated. So everything up here is going to be considered supersaturated. And then everything below is going to be considered unsaturated. So at that point we can still add more in there before a solid starts to form and we have way too much of our solute in our solvent. So that is the 3 different zones on the solubility graph. Let's look at our next slide. We're going to figure out how to read these. What do you notice happens to the solubility as temperature increases? Well, as temperature increases, we're going from left to right on the graph, and each of these curves are going to increase as well. So, as temperature increases, so does solubility. Solubility increases. Okay, what phase of matter are all of these? Sodium chloride is our most common one. That is table salt. So you know that this is going to be a solid. So as temperature increases, solid solubility will also increase. But if you look at gases, this is what it's going to look like. As temperature increases, they are facing down, so they are negative. And what phase of matter are all of these? We know that carbon monoxide, oxygen, helium, those are all gases. So the opposite could be said for solubility of solids versus solubility of gases. As temperature increases, solids are more soluble. As temperature increases, gases are less soluble, so they're completely opposites of each other. Here are some examples. How many grams of potassium nitrate can be dissolved in 100 milliliters of water at 60 degrees Celsius? So, for every 1 gram of water, there is 1 milliliter of water. Okay, so if it says 100 milliliters of water, it really means 100 grams, which is what our graph is going off of, so that's perfect. We're just finding our substance, potassium nitrate, at 60 degrees. So 60 degrees on my graph is here, and we're finding potassium nitrate, KNO3. We're going to go up all the way at 60 to where KNO3 hits that line. Get out of here. Okay, so that is going to tell us how much we have. We're going to go all the way over to see exactly how much that would be. It's kind of above the 100 line. I would say that would be about 102 grams of potassium nitrate in 100 milliliters of water at 60 degrees Celsius. So the left side tells us how many grams that would be. Our second one says how many grams of potassium nitrate will saturate 100 milliliters of water at 10 degrees Celsius. So 10, we're still finding KNO3 at 10 degrees Celsius. KNO3 is right there on that line. So we're going to go over, and that looks like it would be about 22 grams of potassium nitrate. So that's a huge difference. That curve is really steep. So in 100 milliliters of water, 22 grams is going to saturate. Notice it says saturate, so we are going to find where the line intersects. Number 3, how many grams of potassium nitrate will precipitate or fall out of the solution? So that means we're going to be above if 100 milliliters of a saturated solution of potassium nitrate at 60 degrees Celsius is cooled to 10 degrees Celsius. So we have at 60, it is 102, which we figured out before. Okay, so at 60, it is 102 grams. At 10, it is 22 grams. And so we're going to figure out what's the difference between those two from temperature to temperature. So we're going to take 102, we're going to subtract 22, we're going to get 80 grams of KNO3 is going to precipitate out of our solution. So we find one and then find the other and be able to take the difference of those. Okay, so let's look at our next examples. We've got 100 milliliters of water at 50 degrees Celsius can hold how many grams of ammonium chloride? Okay, so we're still going off of our actual graph. It's 100 grams. So we're finding 50 degrees Celsius with ammonium chloride. Ammonium chloride is NH4Cl at 50 degrees. NH4Cl is right there, and that looks like it's right on the dot of 50 grams. So that's our answer. 100 milliliters at 80 degrees Celsius can hold blank grams of potassium chlorate, KClO3, at 80 degrees. 80 degrees, our KClO3 line intersects right there, which looks like it's 40 grams, which is a good, easy number. Okay, I'm going to change colors. We have how many grams of sodium nitrate will precipitate out of a 100 milliliter solution of sodium nitrate if the solution is cooled from 80 to 50. Okay, sodium nitrate is NaNO3. We're starting at 80 degrees. NaNO3 at 80 is there, so that looks like it is 145 at 80. It's 145 grams. And then at 50, it looks like it is at 115 grams. So we're going to figure out the difference if it stays on that saturation line between 145 and 115, which gives us 30 grams. So 30 grams of sodium nitrate will precipitate out. If 50 grams of potassium chloride are dissolved in 100 milliliters of water at 55 degrees Celsius, will the solution be saturated, supersaturated, or unsaturated? So it says 50 grams of potassium chloride at 55 degrees. Potassium chloride is KCl. 55 degrees is here. 50 and 55 intersect there. KCl's line is there. So we are going to be above the line, which means that we are supersaturated at this point. At 40 degrees Celsius, how much potassium nitrate will dissolve in 500 grams of water? We changed the amount of water that we have. So potassium nitrate at 40 degrees is going to be 61 grams, but that is out of 100 grams. Remember, our graph is 100 grams. So we're going to put this in a proportion. At 500 grams, how much would that be? So let's punch it into our calculator. We've got 61 times 500 divided by 100 gives us 305 grams. So 305 grams is going to dissolve of potassium nitrate at that temperature and that mass amount of water. At 10 degrees Celsius, which salt is the most soluble? So if we're looking at this graph, the most soluble will be at the top and the least soluble will be at the bottom, because if it's the most soluble, it takes a great amount of solutes to be able to reach a saturation point. If it's least soluble, it doesn't have a whole lot of that solute to be able to make it supersaturated, where a crystal is going to form. So you can dissolve more if it has a greater amount. So at 10 degrees Celsius, let me go to a different color here. At 10 degrees Celsius, we're going to see which one is the most soluble. Wow, we've got a curve all the way up here. There's nothing above that at 10 degrees Celsius. So potassium iodide, Ki, which is potassium iodide, is the most soluble at 10 degrees Celsius. If I went too fast for any of you, you are welcome to pause this. You're welcome to back it up. You're welcome to re-go over it. But it is extremely important that you understand how to read a solubility graph and what all of these definitions are. So please make sure that if you need to redo this video, go back and do it again. Feel free to do that. It is extremely important that you guys are aware of this information and are able to do it on your own, because our test will be this week. I will be back in class tomorrow, and we will be doing another set of notes tomorrow. So make sure that you're prepared for that. Y'all have a great day. I'll see you tomorrow.